Hello everyone, this talk is about the automated control application for maximizing renewable generation, without any system anomalies. In the other word, it is a remedial action scheme, or RES, that minimizes the wind generation curtailment when the power grid is subject to operational violations. This project is supported by the Advanced Research Projects Agency, Energy. With more and more wind energy integrated into the power grid, the wind energy has provided around 30% of all new installed generating capacity in the United States, at no fuel cost. According to the characteristics of wind turbines, there is more wind energy generated at higher wind speed. In a weak grid, increases in generation outputs may possibly cause system operational violations, such as line overloads or voltage violation issues. And any operational violations may trigger protection systems to operate for secure operation, such as tripping and overloading line. These operations may eventually lead to cascading failures and blackout. Therefore, we need remedial action schemes, RES, to achieve automated controls on the grid. Our proposed RES is designed to prevent overloading conditions on any lines or power transformers, to prevent voltage violation issues, and as well to provide RES functionality of distributed computational modules with resiliency.
Our objectives for wind curtailment RES application consists of three major aspects: optimality, fast responsiveness, and resiliency. To achieve that, we develop the RES application to minimize total amount of wind generation curtailment, to execute within couple of seconds considering grid dynamics, and to provide energy to critical loads even in extreme failures.
To achieve the optimality, we developed the RES application implemented in DC optimal power flow based model and AC optimal power flow model. For DCOPF, it is a linear programming problem that minimizes the wind generation curtailment. This linear programming problem considers the DC power flow constraints and active power line rating constraints. For ACOPF, it is a nonlinear programming problem that achieves the same objective. In this problem, we consider AC power flow constraints, operational limits on voltage magnitudes, and MVA line ratings. In field, we have sensors and controllers installed to achieve the RES functionality. Now the problem is, how do we secure the communication between the sensors and the controllers? In our implementation, we leverage an application platform called Resilient Information Application Platform for Smart Grid, or RIAPS. This is a platform designed for secure communication on smart grid applications. For example, in our application, we use 3 nodes to implement the optimal wind curtailment RES functionality. The RIAPS controller is responsible for deploying the application to 3 distributed nodes. When the application starts running, PMU will start streaming real-time data packets under IEEE 37118 protocols. Then the application is running to solve the wind generation curtailment problem, and execute the control commands to the wind farms. By using this platform, the communications between different actors are secured. To simulate the wind curtailment RES application, we built a hardware-in-the-loop simulation testbed. This hardware-in-the-loop testbed runs the real-time simulation of IEEE 14 bus test system using RTDS, the real-time digital simulator. Our testbed is also developed to stream PMU real-time data using hardware PMU, such as SEL421 and software PMU, like GTNet PMU card. And the testbed is designed to execute RES control commands under TCP/IP socket protocols. In our distributed applications, the RES application is deployed on 3 BeagleBone boards, which are the computational blocks for RIAPS platform. For each node, it runs 3 RIAPS actors: PMU data adapter, decentralized state estimator, and RES actuator. The PMU data adapter is responsible for getting the data packets from PMU under IEEE 37118 protocols. It parses PMU data into measurement message to transmit to the state estimator. When the state estimator receives the message, it will process the measurement data and estimate the system states in its region, then send the state's messages to the RES actuator. The RES actuator among different regions will communicate to each other, in order to find an optimal solution on wind curtailment amounts. Finally, the control command will be sent to the controller to curtail the wind generation output. Here is the implementation of cyber-physical testbed in our Smart Grid Demonstration and Research Investigation Lab, at Washington State University, in Pullman, Washington. Now we are going to show the demonstration of our developed minimal wind generation curtailment RES application running on the RIAPS platform. First, let's start with a dashboard that monitors critical states on the grid. This section monitors the generation outputs on 3 wind farms. We can see the generation amounts are 40 megawatts, 68.6 megawatts, and 78.5 megawatts respectively. Here is the section monitors the power flow on the system branches. We consider the branch from bus 3 to bus 4 and the branch from bus 7 to bus 9 in this demo. We set the different overloading thresholds based on the line ratings on these branches. In these two sections, we can monitor the per unit voltage values on different buses, and we say that the normal operational limits of voltage magnitude should be within the range between 0.95 per unit and 1.05 per unit. This section additionally monitors the active power injection from the slack bus. Now we have the RTDS running to simulate the IEEE 14 bus system. We can see there are 3 wind farms generating 40 megawatts, 100 megawatts, and 78.5 megawatts respectively. In this simulation, overloading conditions appears on branch 3 to 4 and branch 7 to 9. We can also notice there also exists voltage violations at this moment. On the dashboard, we can see that branch 3 to 4 is under warning overloading condition, and branch 7 to 9 is under critical overloading condition. The voltage magnitudes on bus 9 and bus 14 violate the operational limits between 0.95 and 1.05 per unit. Now we can deploy our minimal wind curtailment RES application. Now we can notice is that the PMU data adapters start running to parse data packets, as shown on the deployment journal window. Back to RTDS, we can see that the RIAPS application executes the optimal curtailment amount on the wind farm generation. Wind farm 3 is curtailed to around 70 megawatts. And the overloading conditions is eliminated on branch 3 to 4 and branch 7 to 9. On the dashboard, we can see the power flow on both branch 3 to 4 and branch 7 to 9 drop below the threshold. Voltage violations for bus 9 and bus 14 are also eliminated. The grid is back to the normal secure condition, with all system state variables within the operational limits. Overall, with RES applications developed using RIAPS platform, we enable the economics, reliability and resiliency on the smart grid. In this video, we demonstrates the minimal wind curtailment RES application running on the RIAPS platform. Without proper RES control, the system may subject to line tripping, or even cascading. This might eventually result in blackout, and the society will encounter economic loss. With wind curtailment RES application deployed, We can prevent line overloading on the grid caused by surging wind generations, and provide RES functionality, with secure communication and resiliency.
Even though this demonstration focuses on wind curtailment problem, we can also extend the RES applications to solve any data-driven analytics, distributed computing, coordination and optimization problem in the power grid.